Hey there, and welcome. Today, we're going to crack open one of the fundamental rules of the universe. And we're going to do it using something you probably use every single day, your refrigerator. We're about to tackle a classic physics puzzle that really shows you the surprising power of the first law of thermodynamics.
Okay, so let's just dive right in. Picture this. You've got a room that's perfectly sealed off from the outside world. No air getting in or out. It's also perfectly insulated, so no heat can escape. You put a fridge in there, you plug it in, and then you just leave the door wide open. What happens to the temperature in that room? Seriously, take a second. What does your gut tell you? Most people's brains go to one of two places. The first one is, well, the room gets colder, duh, that's what a fridge does. But then there's the other thought. Maybe it gets warmer because you can hear the motor running and feel the heat coming off the back. And that's what makes this such a great puzzle, right? Both sides kind of make sense. To find a real answer, we're going to need a better toolkit.
So let's build that toolkit. To really get to the bottom of our fridge mystery, we've got to gear up a little bit. First, we need to get a solid handle on what energy actually is. So, at its most basic level, energy is just the ability to make things change. And it's not just one thing. It's a master of disguise. It shows up in all these different forms. There's thermal energy, which is what we feel is hot or cold, mechanical energy, like a spinning wheel, the electrical energy that powers our world, and even chemical and nuclear energy, which is all locked up inside of atoms. Okay, and here's a super useful way to think about all this energy. We can split it into two big categories. First, you've got macroscopic energy. Think of this as the energy of the whole system working together, like a car speeding down the road. It's organized, it's unified, kind of like an army marching in perfect formation. But then you've got microscopic energy. This is the energy inside an object, the chaotic, random jiggling of all its molecules. That's more like a disorganized crowd of people running in every direction. And believe me, this distinction is going to be key. And it gets even cooler because that internal microscopic energy, it's got layers to it. It's made up of what we call sensible energy, which is tied directly to an object's temperature. Then there's latent energy, which is involved when something changes state, like ice melting into water. And it even includes the chemical and nuclear energy that holds the very molecules together. So when we say something is hot, what we're really talking about is all this complex internal energy.
Okay, this leads to a really, really important distinction. In the world of physics, the word heat means something very specific. It's not something an object has. It's energy in the process of being transferred. And it only happens for one reason, a difference in temperature. If you have two things at the exact same temperature, there is zero heat transfer between them. Simple as that.
So you might be asking, if energy is moving, but it's not because of a temperature difference, what do you call it? Well, that's what we call work. Think about the electricity flowing through the power cord into the fridge, or a fan blade pushing air. Those are forces making something move. It's a pretty simple rule of thumb, really. If an energy transfer isn't heat, it's gotta be work.
So there you have it, the two big ways energy gets around. You've got heat, which is a disorganized energy transfer, all driven by that random chaos of temperature. And you've got work, which is an organized energy transfer, driven by forces like electricity. Now that we have these tools in our belt, we are ready. We can finally solve this thing.
All right, we've got our concepts down, heat and work. Now it's time to unveil the one rule that governs everything we've been talking about. This is the absolute, non-negotiable law of the universe that will solve our refrigerator puzzle once and for all. And here it is, the first law of thermodynamics. This is, no joke, one of the most fundamental principles of reality. It states, simply, that energy can be neither created nor destroyed during a process. It can only change forms. This isn't a theory or a guideline, it's a cosmic law. Energy can't just pop into existence or vanish into nothing. It just changes its costume. And what's great about this law is it gives us a super simple way to keep track of everything. It's an energy balance. Think of it just like your bank account. The money that comes in minus the money that goes out equals the change in your balance. For energy, it's the exact same idea. Energy in minus energy out equals the change in the total energy of the system. Okay, let's do this. Let's apply this logic to our room, step by step. First, what's our system? It's the entire sealed room, including the air and the fridge itself. Now, what energy is coming in? Well, you've got electricity, that's work, coming in from the wall socket to power the fridge. What energy is going out? Absolutely nothing. Remember, the room is perfectly insulated. So if we have energy coming in, but zero energy going out, what has to happen? The total energy inside that room must go up.
And the answer is the room actually gets warmer. I know, it feels counterintuitive. See, a fridge is basically just a heat-moving machine. It uses its cooling system to pump heat from inside the box to the coils on the back. But since the door is open and the coils are in the same sealed room, you're not actually removing any heat from the room. You're just moving it around. On top of that, all that electrical work the motor is doing, it's got to go somewhere, right? The first law says it can't just disappear. It gets converted into, you guessed it, more heat. You've essentially just plugged in a really, really inefficient space heater. Okay, hold on. This actually brings up a brand new puzzle, a really interesting twist in the story. If energy is always conserved, if the total amount never changes, why do we care what form it's in? This brings us to a huge idea, the difference between the quantity of energy and the quality of energy. And here's the paradox that might be bugging you right now. The first law just told us that the total quantity of energy in the universe is constant. So why are we always being told to conserve energy? If it can't be destroyed, what exactly are we supposed to be saving? And the answer is, we're not trying to save the amount of energy. We're trying to save its quality, its usefulness. High-quality energy, like the organized flow of electricity, is amazing. You can use it to do almost anything. But once it gets converted into low-quality, disorganized energy, like the waste heat from the back of our fridge, it's much, much harder to do anything useful with it. The total amount is the same, but its value has plummeted. Want a perfect, everyday example of this? Just think about your car's engine. You put in $100 worth of high-quality chemical energy in the form of gasoline, but only about $25 of that actually turns into useful work that moves your car forward. The other $75? Poof, they're just degraded into low-quality waste heat that radiates out from the engine. The energy is still there, but most of its quality is just gone. And look, this isn't just some abstract physics concept. This idea of energy quality or efficiency hits you right where it counts, your wallet. Let's see how this plays out with things you use every single day.
Let's start with something simple, lighting. This table shows what we call efficacy, basically how much light you get for the electricity you pay for. Look at that old-school incandescent bulb. It's terrible. Most of the energy it uses is wasted as heat, not light. Now look at a modern LED. Whoa, it can be more than 8 times more efficient, giving you the same amount of light for a tiny fraction of the electricity and the cost.
Or how about this? You want to cook a casserole. A standard electric oven will get the job done for about 19 cents worth of high-quality electricity. A gas oven is a bit cheaper, but the microwave? Look at that. It's an absolute game changer. It's so efficient at targeting its energy that it costs just 3 cents to do the same job. It just shows that how you choose to use energy really, really matters.
And this is where it all starts to click together, right? All these individual choices we make every day, which light bulb to buy, which oven to use, they don't happen in a vacuum. They all scale up, and our collective energy use has a massive footprint on the entire planet. So what is this number? 5,443 kilograms. That's the average amount of carbon dioxide that gets pumped into the atmosphere from a single typical car every single year. All that inefficiency, all that waste heat we talked about has a real consequence. It's a powerful reminder that our energy choices have a global impact. And that leaves us with one last question to chew on. We often hear an electric car called a zero-emission vehicle. And yeah, at the tailpipe, that's true. But we just learned from the first law that you have to look at the whole system, right? Energy doesn't just appear out of nowhere. That electricity has to be generated somewhere. So the bigger, more important question is, what's the footprint of the power plant making that electricity? It's the perfect reminder that when it comes to energy, there's always a bigger picture.